Last talk by Ramón Plaza and from here and from Universidad Nacional Autónoma de Mexico. And we will speak about dissipative structures of Korteweg system for compressible fluids with viscosity and capillarity.
Thank you very much. Well, first of all, I would like to thank the organizers of this conference for the opportunity to talk and to participate in Volker's 60th birthday. I'm very happy to be here. I'm going to talk about the dissipative structure of what they are called Korteweg systems for compressible fluids that exhibit viscosity and capillarity. This is actually a very simple stuff. What I want to communicate in this talk is an idea more than actual results. Of course, I'm going to talk about some results specialized to Korteweg fluids, but the main point is to talk about this dissipative structure concept, which is very well known in the case of purely viscous or relaxation systems, but that can be extrapolated to higher order systems. I hope that you find it interesting. This is joint work with José Manuel Valdominos. Actually, this is part of his PhD thesis. He has defended the thesis. He's now going to France. And with Felipe Angeles, it's an extension that we have recently found with Felipe and José Manuel. And of course, we have to thank our sponsors for the work that we have done. Okay, so this is the structure of my talk. First, I'm going to talk about the well-known Kawashima-Shisuta theory, which is a concept of dissipative structure for viscous systems. And then I'm going to talk about the extension of Jeffrey Humphreys to higher-order linear operators. And then how can we apply these concepts to the Navier-Stokes Korteweg system, which is the asymptotic fluid with viscosity and capillary, and later on to the Navier-Stokes Fourier-Korteweg system, which is the non-isentropic energy exchanging case. Okay? So what we did with Jose Manuel was actually to push Humphreys' observations at the linear level to the nonlinear level. In these both cases, in the isentropic case, everything was smooth. And in the non-isentropic case, there is a little twist from physical theory that I will let you know. Okay, so what is the Kawashima-Shisuta theory? We are considering regularizations of hyperbolic systems of conservation laws. Or the paradigmatic case is Euler equations for fluid dynamics. You have a hyperbolic system, and of course, as you well know, singularities occur, shock waves, relaxation waves, etc. There is no global existence of smooth solutions. Even with smooth initial conditions, you can have these structures. So in the physical theory, what you do is to regularize your hyperbolic system with some dissipation mechanisms. So these dissipation mechanisms can be of relaxation type, right? Viscosity, dispersive terms like capillarity, etc., or even higher order terms. So in the mid-80s, Kawashima and Shisuta found the right conditions for what is called the dissipative structure of these systems. I mean, when you add viscosity, you expect to dissipate your system, right? However, as you know, in fluid dynamics, the first equation is always hyperbolic in a certain sense because it's always equal to zero. The right-hand side is equal to zero. Mass is conserved. So this equation is always hyperbolic in a certain sense. So what you add is a viscosity tensor that has a kernel. When you add artificial viscosity with strictly parabolic viscosity terms, everything is fine because it's a uniformly parabolic operator, right? So the idea is, in what sense is this viscosity that I am incorporating into the system actually dissipating the solutions? So this was done by Kawashima and Shisuta in the 80s. They developed a theory I will tell you in a second. And then in 2005, my colleague and friend Jeffrey Humphreys extended, at least at the linear level, this concept for higher order systems. This paper, in my opinion, has been overlooked in the literature. It was published 20 years ago, and it has been only cited by Felipe, myself, Jose Manuel, and that's it. I will tell you about the contributions of Jeffrey. And even though he didn't push the theory to the nonlinear level, I believe that this is a very important contribution to the theory. The applications include, of course, fluid dynamics, reaction diffusion systems with transport terms, thermal relaxations, fluid with capillarity, etc. So let me explain what is this viscous dissipative structure of a viscous system. In the case of one-dimensional systems, I have to tell you that all this theory can be extrapolated to multi-D. But I will, for simplicity, specialize the discussion to one dimension only, okay? So these systems with viscosity, they have this form. There is a left-hand side, which is a divergence in time and space. This is a nonlinear transport term, of course. And this B is a viscosity tensor, so you are adding second-order dissipation terms. U is a vector of state variables. F is a nonlinear flux, or the nonlinear transport. And B is a viscosity tensor. As I mentioned, for physical considerations, for example, compressible Navier-Stokes, fluid dynamics, we are interested in the case in which B is not a positive definite, but at least semi-definite positive. Positive semi-definite, sorry, okay? So this viscosity tensor has a kernel. We have to compare with the solutions of the implicit system. What happens if B is equal to 0? Then you have, for example, Euler equations, okay? And you say that the system is hyperbolic if the Jacobian of the nonlinear transport term is diagonalizable over R, which means that all the eigenvalues are, for every U, are real and semi-simple. What is the motivation for this definition? It's actually very physical. The idea is that if you linearize, for example, around a constant state, you can have traveling wave solutions to this. So it is a necessary condition for the implicit system to be well posed in L2, for example, and it guarantees traveling wave solutions. So if you consider a traveling wave solution of this system, what you obtain is an eigenvalue problem. Okay? Now, what is the discovery of Kawashima in the 80s? Well, they introduced this concept of genuine coupling. So they say, well, the viscosity tensor will strictly dissipate the solutions, provided that no eigenvector of A, of U, for every U, lies in the kernel of B of U, which is actually very simple. It's an algebraic condition. Okay? This property is called genuine coupling. It's also known as the Kawashima condition or Kawashima-Shisuta condition, or simply the K condition in the literature. So heuristically, it's very physical, right? It's very simple to understand, because if you consider a solution of the hyperbolic system, and if you add dissipation, and if you still have hyperbolic waves that are solutions of the viscous system, then your viscosity is not dissipating anything. For example, suppose that you linearize around a fixed state, which is a solution, because it's an equilibrium solution. So what you get is a very simple hyperbolic system with constant coefficients. And suppose that lambda is an eigenvalue of A, which is a constant matrix. There is an eigenvector, okay? So you can construct traveling wave solutions of this form. There is a profile function that depends on the phase in the direction of one of the eigenvectors. So if you substitute in the linearized viscous system, what you get is an equation like this. So this is the motivation for the concept of strict dissipativity. If you have a solution, if you have a vector B, which is an eigenvector of A, which is also in the kernel of B, then you will have a hyperbolic wave, so to speak, that is not regularized or is not dissipated by the viscosity. So this is actually very simple. It's an algebraic condition. It's a linear algebra condition. The important point of this definition is that the consequences are far-reaching, are not only at the level, not only at the linear level. So what are the consequences of this? Well, another condition that is very important that Felipe talked about yesterday is about symmetrizability. So the classical definition of a symmetrizer for this kind of systems is the Friedrichs definition. So we say that the system is symmetrizable in the sense of Friedrichs if there exists a smooth, symmetric, positive, definite matrix that depends on U, such that if you multiply the hyperbolic part, A, on the left, and the viscosity part as well, they are both symmetric. And this is very helpful to close energy estimates. It is very well known that Friedrichs symmetrizability implies hyperbolicity of the underlying hyperbolic system, and this is not only mathematical, it has a very important physical interpretation, and is the following. Usually when you have an entropy function associated to the hyperbolic system, usually the Hessian of the mathematical entropy is your symmetrizer. For example, in compressible Navier-Stokes, the mathematical entropy is minus the physical entropy. If you take the Hessian of that, you obtain a symmetrizer for the compressible Navier-Stokes equation. Okay, so let me introduce the concept of strict dissipativity. So suppose that you have a generic viscous system in quasi-linear form, like this. Suppose that you have an equilibrium state, U bar. You linearize your equation around this solution, and you get a system with constant coefficients. So now A bar and B bar are constant matrices. This is the nonlinear part. We are going to disregard this for the moment. Suppose that your system is Friedrich symmetrizable. Then you multiply by your symmetrizer on the left and you obtain a symmetric system. Well, this is constant coefficient, so you take the Fourier Laplace transform and you obtain an algebraic equation like this. Okay? So the concept of the strict dissipativity is the following. The linear system is said to be strictly dissipative if all the solutions of this spectral problem satisfy the following, that the real part of lambda that depends on the frequency, Fourier wave number, have a negative real part. And as I mentioned, the genuine coupling condition is the following. The system is genuinely coupled if no eigenvector of A is in the kernel of B. Okay? Well, the contribution of Kawashima is also related to this concept. He introduced these objects. He called them K because of Kawashima. Okay? So we're going to define a compensating matrix function for the system, K, if satisfies the following. K times A0 is skew-symmetric. The symmetric part of K times A, which is this matrix A, okay, is already symmetrized, okay, it's already symmetric. Plus B is positive definite. This is what encodes the diffusion, the dispersion. Here, this S is the symmetric part of the matrix, okay? So what is the contribution of Kawashima to the theory? Well, that these last three concepts are equivalent. So this is the equivalence theorem of Kawashima and Shisuta. Under the same hypothesis, you have a viscous system of conservation laws, you linearize, etc. Suppose that it's already symmetrizable under symmetry assumptions. Your symmetrizer is positive definite, your viscosity tensor positive semi-definite. The next statements are equivalent. The system is strictly dissipative, the real part of lambda negative. The system is genuinely coupled. The system admits a compensating matrix. And then another piece of information, there exists a constant such that the real part of lambda is actually controlled by this term. This estimate actually gives you the decay rate of your solutions at the linear level. That can be extrapolated to the nonlinear level in some cases. So what I was mentioning is that the consequences are far-reaching. So this dissipative structure implies a nonlinear decay structure for solutions to the nonlinear problem. So this is a very important property in physical systems. You have an equilibrium state, and you want to know if this equilibrium state is stable under small perturbations. So you perturb your nonlinear equations with a small perturbation, and these linear decay estimates allows you to prove that the solutions exist globally in time and they decay. So you are adding a small energy perturbation to your equilibrium system, and then the perturbation fades out in time. So these decay estimates can be performed at the lowest level, the linear level, and then the small nonlinear terms, of course, can be handled via local existent theorems and absorbed into the linear energy estimates. Not only that, but also if you consider traveling wave solutions, viscous shock profiles, for example, or relaxation shock profiles, if they have a small amplitude, then you can consider a Kawashima type of estimate in the neighborhood of these small waves, okay, and prove the stability of these shock profiles using this type of estimates. This can be done in the case of viscous shock profiles, relaxation zone profiles, and even in radiative hydrodynamics, when the regularization is via coupling with an elliptic equation. So this is essentially the theory that Kawashima and Shisuta developed, and then they introduced a further classification of the systems later on. They call it strictly dissipative of type P and Q if this inequality holds. for a strictly dissipative system. They say that the system is of standard type when P equals Q, of regularity loss type when P is less than Q, and regularity gain type if P is greater than Q. They do it like that because 1, 0, when P is 1 and 0, Q is 0, is precisely the decay rate of the Hute kernel. I really don't like this classification because it's a bit misleading. They are not talking about the regularity of the solutions at all. It's just comparison of the decay that you have with respect to other well-known linear equations. But anyway. Okay, so let me talk about Jeffreys' extension. In 2005, Jeffreys posed the following problem. So he said, okay, so let's suppose that you have a linear operator of any order with constant coefficients. This is an operator of order M, okay, with decay constant matrices. So it's a constant coefficient problem. You take the Fourier Laplace transform, and then you obtain an equation like this. And this is, in my opinion, one of the first clever ideas of Jeffrey. So he said, okay, let's take the symbol after the Fourier transform, and let's split the symbol into the odd part of the symbol, which is like a generalized transport term, and the even part of the symbol. Just like that, okay? And he goes further and say, I'm going to mimic Kawashima's theory when the viscous is only one term, which is second order, and the transport term is only one term, which is first order. So I'm going to mimic everything that Kawashima did with this new generalized viscosity and transport. So he defines a strictly dissipative if these solutions have real part of lambda negative, and he extends the genuine coupling condition to these higher order operators by saying no eigenvector of the symbol A, which now contains all the odd terms, lies in the kernel of the symbol B, which contains all the even terms. And the second clever idea by Jeffrey is the following. Well, you need some symmetrizability of some sort, right? So let's suppose that you have not a Friedrich symmetrizer, but a symbol symmetrizer. So let's suppose that you have a symmetric, smooth, positive, definite, real matrix valued function A that depends on psi, such that both symbols become symmetric after multiplication on the left by A0. Of course, the positive semi-definiteness of B remains, okay? And this is very important because not all systems that are symbol symmetrizable are Friedrich symmetrizable. There are many physical systems that are not Friedrich symmetrizable, but can be symmetrized in the sense of Friedrichs, in the sense of Humphreys, sorry. This is important for physical applications. And if you think about it, it's natural because you can find a symmetrizer for a matrix. It's not difficult. Finding a symmetrizer for the transport and the viscosity can be complicated in some sense. But if you need a simultaneous symmetrizer for the transport, viscous, and capillarity, for example, term, that can be impossible, even in very simple systems. So this notion of symmetrizability was very, very natural. Symbol symmetrizers are known for many years, no? But I don't know why nobody had thought about this when dealing with higher order terms. So this is the second contribution of Jeffrey. And he, of course, extended the definition of a compensating matrix function, which is the existence of now a symbol, okay, that has these properties that K times the symmetrizer is skew-symmetric and that this positivity condition holds. And he proves a theorem which is very similar to Kawashima's at the linear level, okay? These conditions are equivalent. L is strictly dissipative, genuinely coupled, the existence of K and this estimate. There is an assumption that he introduces, and he needs that the hyperbolic system has constant multiplicity, meaning that all the eigenvalues of the symbol A have constant multiplicity for every xi. This condition is not can be disregarded. Okay. Okay. Let me make a comment about Humphreys' proof. Humphreys provides an explicit formula for K. It's actually the Racine inverse of this commutator operator. So, for example, if A is any complex matrix which is semi-simple with different eigenvalues and certain multiplicities, you take the eigenprojections and you define K like this for every B, for different eigenvalues, lambda I and lambda J. Then this is the Kawashima, I'm sorry, the compensating matrix function. Okay. Okay. So now, with Jose Manuel, we noticed that this paper has been completely overlooked, and I said to him, okay, there are these systems, physically motivated, Navier-Stokes-Korteweg and Navier-Stokes-Fourier-Korteweg systems. Let's try to apply Humphreys' definitions and try to push it to the nonlinear level. We could do it with no problems in the case of Navier-Stokes-Korteweg system, and we found some physical problem that we had to handle in the non-isentropic case. But let me talk about first the Korteweg, the isentropic. So consider the equations of isentropic compressible fluid dynamics in Lagrangian coordinates. V is going to be the specific volume, U is the velocity, okay? Specialized to one dimension, of course. And then the system looks like this. The first equation, as I mentioned, is always equal to 0 because it's mass conservation. The second equation is the equation of conservation of momentum. And it has this structure. There is P, which is the pressure. Okay, so this is going to be the nonlinear transport term with this minus here and this P. And then there is a viscosity term, physical viscosity. Mu is actually a viscosity coefficient that depends on the specific volume. So this is a thermodynamic potential, right? And then there is this term here that accounts for capillary effects. So there is a capillarity coefficient kappa here that depends on the specific volume as well, and encodes third order terms, as you can see. Okay. The thermodynamics, well, we have the specific volume in a positive domain, okay? P prime has to be negative in order to assure the hyperbolicity of the left-hand side. And mu and kappa are positive, smooth, and thermodynamic potentials depending on B. A very important observation, this is a one-dimensional isentropic version of the system derived by Dunn and Serran in the 80s to describe compressible fluids with internal capillarity. Here, P depends only on V. Okay? So let's do exactly as Jeffrey remarked in his blueprint. Consider a constant equilibrium states, U bar, B bar, then you consider perturbations, you have a nonlinear equation, nonlinear system, and you need some local theorem for the existence of the solution. So the local theory is well understood, is well known since 30 years ago by the work by Hattori and Lee, Danchan and Desjardins, etc., and other people. So you have this result. Suppose that you have perturbations of your constant state that belong to these Sobolev spaces. Here you have high regularity in V because it's the specific volume, and your system is of third order in the specific volume, okay? And the derivatives are in L2 in time, etc. And of course, you are avoiding vacuum. So you're assuming that you are away from 0. This is a very classical result, sorry. This is no surprising. We have high regularity. S is greater than 3. So you obtain actually classical solutions thanks to Sobolev embedding. So you define this energy here, and then you have this theorem, which is a local theorem. Under the assumption, suppose that you have initial conditions in HS1 and in HS S greater than 3, and if you can find a constant such that this is bounded, then you obtain a unique smooth solution for the whole system, where B and U are now perturbations that exist in this space and satisfy this energy estimate. This is actually very classical. Okay, good. So now we linearize this system around this U bar and V bar. You obtain a constant coefficient system, very simple, with the matrix here and another matrix for the viscosity and capillarity terms with constant coefficients. Okay, so you take the Fourier Laplace transform, well, in this case only the Fourier transform. Okay, and then you can write it like this operator, higher order, in this case third order. And if you take the Fourier Laplace transform, the corresponding symbols are like this. Notice that here the transport is incorporating the capillary term. Okay, so now we have, this is the transport term, and this is now the capillarity term. And this is the viscosity term, the same as before. This is not symmetric, of course. This is not symmetric. But, well, this is symmetric, but this is not. But this system is very simple to obtain a symmetrizer. It's actually a 2x2 matrix. And the simple symmetrizer is simply diagonal, with this beta given by this number, depends on the Fourier wave number here, but it's always positive. So this is actually a symmetrizer for the symbol. It is very simple to check that this simple system with 2x2 matrices is not Friedrich symmetrizable. It's not symmetrizable in the sense of Friedrichs. You cannot find a matrix that symmetrizes the three 2x2 matrices. This is a linear algebra for your students as a homework, no? Prove that it's not symmetrizable. But it is symmetrizable in the sense of Humphreys. Very simple. Now you symmetrize your system, okay? And then you can show that the linearized Korteweg operator satisfies the genuine coupling. It's very simple to check that no eigenvalue of the hyperbolic part lies on the symbol of the dissipation, followed by direct computation. So you introduce a change of variables and then obtain this equation for this new variable B with these symmetric symbols, okay? And you can obtain the compensating matrix function by inspection. I mean, you can use Jeffrey's formula, works, but it's actually easier to obtain the compensating matrix by inspection. This is skew-symmetric, okay, and satisfies all the assumptions of Humphreys. I'm making this observation because actually there is a degree of freedom in the choice of the compensating matrix function because it's now a symbol. So there are many ways to find the compensating matrix function. And this one, by inspection, satisfies these uniform bounds. And these uniform bounds will allow you to actually obtain a better decay rate for the lambda that depends on psi, just for practical purposes. So now let me show you how to get the basic energy estimate, which is at the pointwise level, for the solutions of this linear system. And this is how the compensating matrix function works and plays a role. So the solutions to the system before this one here satisfy this pointwise estimate. And the decay rate is actually exponential. And I want to show how to do this because it was Kevin Zumbrun who pointed out this. We were in his office, we were on the blackboard, and he told me, pay attention, Ramon, because this works like magic. It's actually very nice. It's a pointwise estimate. It's actually very simple. Okay, so let's take the inner product of the equation for V hat with V hat. So you get this relation, okay? Remember, this is the equation for V hat, okay? So you obtain this relation and multiply the same equation but minus Ixi k, which we know that is skew symmetric, and we obtain this relation, okay? Since k is skew symmetric, well, this is the real part, okay? The real part. Since Q is skew symmetric, then the real part of this equation, I mean, of this term here, is actually the derivative of somebody. And then taking the real part of the previous equation, you obtain this relation here. Now, using that B is positive semi-definite and that K of A, the symmetric part, is actually symmetric, and that psi K is uniformly bounded, okay, you can obtain this estimate. So you estimate this part by taking any epsilon positive and say C of epsilon depending on 1 over epsilon. Now multiply this equation by any delta and add it to the first equation over here. And the idea is to obtain delta sufficiently small such that this guy here is an energy. This guy here is going to be real because K is skew symmetric. So this is actually an energy that is very similar to the modulus of B squared. So now you have this estimate here, and now, as I mentioned, you define the energy like this. This is real because K is skew symmetric and it's actually uniformly bounded C of A, and then it's actually equivalent to the complex modulus of B squared. It's the same thing. And then here you apply the fact that the compensating matrix function has this very nice property that the K of A symmetric plus B is positive. It's a positive matrix. So you substitute this, take epsilon appropriate, and then you obtain actually the decay of your energy with the decay rate that you need, in this case exponential. Okay? Good. So at this point, I usually remember the song by the Rolling Stones that says, you can't always get what you want, but you get what you need. So this is a very simple physical system in which is not Friedrich symmetrizable. This is what we want, but it's not what we need. So what you need is only symbol symmetrizable because you obtain a very nice decay rate for the solutions to the linear problem. Here you can see 1 plus psi squared to the first component because it's the specific volume, you need more regularity, okay? So with these estimates, you can prove that for the linear system alone, if it's in an appropriate energy space, intersection L1, finite mass, okay? Then you can get this decay rate for the solutions to the linear problem. Now, and the evolution problem. So these are decay rates in T, okay? Exponential here, and then here we have algebraic decay because of the mass. Multiply the mass here. Doesn't work. Okay. Sorry. Follows from the Fourier estimates very easily. Okay. So now you can generate a semigroup. You generate a semigroup with a symbol that you have. You have the semigroup decay for solutions to the linear problem, and then you consider the nonlinear part. So you add the nonlinear terms. So now the nonlinear terms is important for this system that has some divergence form. Actually, the nonlinear terms are conservative in this sense, okay? So it has this structure, and you can bound everything by quadratic terms in this case, okay? And consider an initial condition for the nonlinear problem under the assumptions of the local existence theorem by Hattori and Lee. You have a classical solution for small time, okay? And using the Duhamel formula, you have to estimate this guy here. It's not hard, actually. With the semigroup estimates, you obtain this, and then you define your energy, and you obtain, this is still the variation of constants formula. You need to estimate these terms by using that for HS sufficiently large, you have a Banach algebra and Sobolev calculus, you can estimate these nonlinear terms in HS and in L1. This is not hard. And at the very end, you obtain something like this. This is a bit routine, but it's interesting at some point. You obtain these two integrals. These integrals are very easy to bound. These two integrals are going to be bounded, uniformly bounded for every t. These two because of the exponential decay, and this is an elliptic integral. Well, can be done. I mean, it's, of course, lots of estimates, but it can be done. The consequence is that you obtain an energy estimate for the solutions of your nonlinear equation, and with the help of the local existence theorem, you can iterate nonlinearly to obtain a global solution that decays in time. So this was the first result in the case of the isentropic Korteweg system, right? The perturbations live in a global space, so these are global solutions, and they decay in time. Good, so we were actually happy. We reported this in a paper, and we said, okay, let's go to the next level, which is the non-isentropic case, the compressible fluids with energy exchanges. Okay, and the proof is very similar, but there is a physical twist, as I mentioned, and it's the following. So now consider the one-dimensional Navier-Stokes Fourier Korteweg system in Eulerian coordinates. Now Eulerian coordinates. This is the equation of conservation of mass. Okay, this is the equation of conservation of momentum with the Korteweg tensor over here that encodes the capillarity, and you have to add the energy exchange equation. This is the equation of conservation of energy. This ugly one is the conservation of energy. You have here epsilon, which is the energy density of the fluid, the pressure, of course. Now you have a Fourier coefficient alpha, and again, the viscosity and the Korteweg tensors. So the Korteweg tensor is actually given by this term, and this W here is called the interstitial work that it was derived by Don and Serran in their paper. The viscosity coefficient mu, thermal conductivity alpha, and the capillarity coefficient are strictly positive smooth functions of now two thermodynamic variables, which are rho and theta. But there is an important fact, and is the following. Don and Serran derived this system under the assumption of non-equilibrium thermodynamics. Korteweg proposed the capillarity model by saying, okay, all your tensors will depend now on density gradients. But this extension was incompatible with the Clausius-Duhem inequality from thermodynamics. So if you assume that, you can do some analysis and then check, actually verify that all the coefficients have to be zero. So many years later, 85 years later to be precise, Don and Serran extended under the framework of rational mechanics the model by Korteweg. It is based on an extended version of non-equilibrium thermodynamics, and they added the interstitial work to the equation of energy, this W here, okay? This is actually some micro forces, micro stresses well, this model was developed in the framework of phase transitions. So these are actually interstitial stresses in the interface, in the boundary phase. But the important part is that now the internal energy of the fluid does not depend only on rho and theta, but depends also on rho x, gradient of the density. And has this form. It's going to have a standard internal energy that depends only on rho and theta, plus this term over here. which is actually the non-standard part. This is non-equilibrium thermodynamics because it depends on rho x. And I mentioned this because as we were working, we found many papers, about 10 papers, from serious analysts, people that I know, that don't consider the dependence on density gradients. Just to say something, it's like saying, okay, K, this K here, is going to be 0 in the right-hand side of the system, and it's going to be non-zero on the left-hand side. Because they consider this E as the, this epsilon as the E. They say, okay, this is going to be the internal energy from standard thermodynamics with K equal to 0, and on the other side, they put K different from 0. So I understand the mistake. This is a Pavlovian reflex because we are used to consider equilibrium thermodynamics all along, but this model was derived under the non-equilibrium hypothesis. So this is the energy that we have to consider. So now let me just review the thermodynamical hypothesis. The independent thermodynamical variables are rho and theta, which is the temperature. They belong to a fixed open domain, okay? And the state of variables is precisely the set, I mean, rho and theta positive. This is important assumption. The fluid is specified by the non-standard Helmholtz free energy that has this form, okay? In this is capital, in the font of the slides is almost the same, but this is capital psi and this is non-capital psi over here, okay? So this is the standard part of the Helmholtz free energy, and this is the non-standard part. The specific entropy and internal energy have also descriptions like this: equilibrium plus non-equilibrium, equilibrium plus non-equilibrium. The viscosity and heat conductivity are positive functions of rho and theta. The standard part of the thermodynamic potentials are standard in every sense, so they satisfy the volumetric first law of thermodynamics and the equilibrium by conditions for fluids. And this is our contribution. We are going to further assume that the capillarity coefficient is actually is concave, right? It's a non-stringly concave function with respect to the temperature. And this is a sufficient condition for the non-equilibrium specific heat to be non-negative. The non-equilibrium specific heat has this form. This is the standard part plus the non-standard part. So this is a sufficient condition to have this well-known thermal stability condition for thermodynamic systems under shear. Well, what is the consequence of this? The analysis is a bit more complicated because when you work at the linear level, if you linearize around a constant state, the non-standard part of the thermodynamic potentials vanishes because the derivative of rho constant is 0. But when you have to treat the nonlinear part, you have to take into account all these effects. So now the conserved quantities, which is mass, momentum, and energy density, okay, now depend on density gradients. The fluxes as well. Okay, so when evaluated at a constant state, of course, these vector fields reduce to the standard thermodynamic potentials. So at the linear level, there's no problem, but at the nonlinear level, you have to do something else. So we introduce a new and novel change of variables. This is completely new, but it's actually very natural because now we're going to work with these variables. It's going to be the conserved quantities that depends on gradients of ux, of your density gradients, minus the conserved quantities evaluated at the constant state, and multiplied by this Jacobian, the inverse of this Jacobian. And this Jacobian is going to be, the determinant of this matrix is going to be different from 0, uniformly away from 0, thanks to the thermodynamic assumption that we made on the capillarity coefficients. That guarantees the positivity of the specific heat in the non-equilibrium thermodynamics. Okay, so this is exactly what I was saying. Under the assumptions, the matrix field is invariable, okay, because of our assumption. And then you obtain a linearized, well, this is a nonlinear system for the perturbation W in the new variables. I don't want to bore you with all the details. These are long computations in which over here and over here is precisely the nonlinear terms depending on density gradients. Okay. The nonlinear terms have also a conservative structure, fortunately, and you can push your linear estimates exactly as we did in the isentropic case. Now with bigger matrices, of course, okay? You can obtain a symmetrizer like this, and you can get energy estimates with the help of a smooth compensating matrix function that is also skew symmetric like this, okay? And this is the result that actually you can obtain, right? That the perturbations of small perturbations of an equilibrium state for the non-isentropic Korteweg system also decay. Okay? You have global solutions for the perturbation and they decay in time. Okay? So this can be extrapolated, and further developments include global existence of subsonic equilibrium states for QHD systems, quantum hydrodynamics. And recently, with Felipe and Jose Manuel, we extended all the Humphreys theory to the multi-decays, and we made some technical contributions to the proof because we don't need the hypothesis of constant multiplicity of the transport symbol, which is important for applications. The applications include quantum hydrodynamics, Korteweg fluids in multi-D, and the dispersive Navier-Stokes systems by Livermore and Son to describe the ghost effect in some situations. So thank you very much for your attention, and happy birthday, Falcon.
Question?
Thanks for this beautiful lecture. I would have a question about the decay, the time decay. You first, for the Navier-Stokes Korteweg case, you first obtained an exponential time decay, yes. And then for the nonlinear term, the final result was a decay like t to the minus
right.
1/4. So where do you lose the exponential decay?
Because you actually need to assume that the initial condition is in L1, has finite mass. In order to split the symbol, the energy estimate on the symbol, you obtain actually the norm of u hat 0, and for that it is here where you lose the exponential. So actually the exponential is multiplying the energy, Sobolev norm, and the algebraic decay is multiplying the mass. This is the point where you lose.
Question? No? Well, I will ask one question. When people do and they do not care about when you say the last model, they do not care about K on the left side on the energy. They make the similar studies with all this is what is the comparison to what you get, for example, in terms of global existence, in terms of decays? What do they get really in that?
Well, this is a good question. I don't know. I think that they get better decay estimates, but it's because, I mean, the model is different.
Yeah, okay.
It's actually easier, no? So my comment was not on the mathematical side, it's more on the physical side. So you have to take into account the capillarity on both sides because it's a non-equilibrium thermodynamic system. So, but I think that they obtained something better at the, yes.
And they don't use
remember.
They don't use the same method that you use.
No, actually no. This is an important difference. They actually perform energy estimates at the level of the linearized equations, and then this is a more general abstract framework. You only need to linearize and see if your symbols satisfy some algebraic conditions in order to obtain the decay of the semigroup.
Okay.
Like a more general framework can be applied to many systems.
Okay, and it is due to the first part of the talk that you explained. So
Exactly.
that's the
I think that the
pivotal
main
part of,
ideas, right? The main ideas were Kawashima's and Jeffrey's, and this is propaganda for Jeffrey's work.
I see it. Okay, thanks. Any other question? If not, let's thanks the speaker again. And we start again at